In this lecture, we'll talk about partial Fourier acquisitions and how to reconstruct images from them. Partial Fourier acquisition is probably the oldest the oldest acceleration method, scan acceleration technique, and is still widely used in MR, especially when we only care about the magnitude of the images that we're reconstructing. So first, a little background motivation. Let's consider a full k-space acquisition from a 2D-FT sequence where we're scanning a rectilinear grid in k-space. So there's a couple things we can define here. One is that this total swath across the entire matrix of lines that we are going to acquire is 1 over delta x. The total swath in terms of inverse centimeters is 1 over delta x, which is equal to n times the spacing between the lines. So n here being the matrix size or the number of lines in the ky dimension, and delta k being the spacing between the lines. So here's delta k here, and delta k is further equal to 1 over the field of view. Now let's further say that what we want here is a T2 weighted acquisition. It's very common to acquire both T1 and T2 weighted acquisitions in a given patient scan. So for a T2 weighted acquisition, we want to use a long TR to minimize the T1 weighting and a long TE to maximize the T2 weighting. Let's say then further that we have a field of view of 20 centimeters, which is reasonable for brain imaging, maybe even a little bit small, and we want a resolution of 20 over 128 centimeters. So that's a matrix size of 128 by 128. So how many TRs would we need to make this measurement? Well, the number of TRs is going to be equal to n, the number of lines that we're measuring. That's going to be equal to 1 over the product of delta x and delta k, which is equal to field of view over delta x, which is equal to 20 over 128, which of course is equal to 128. I went through this rather circuitous route to get to this number just to emphasize the relationships between these numbers. If we use a TR of 2 seconds, then how long will this scan be? Well, we can calculate that from the fact that we have a TR of 2 seconds times n, which is 128. That's equal to 256 seconds, which is greater than 4 minutes. And which can be kind of a long time to lie perfectly still. And that's just for a single slice. Now we can interleave the slice acquisitions to a large degree and reduce the time it takes to get a multi-slice volume. But your minimum scan time here is going to be at least 4 minutes, and it'll probably go up to maybe 8 minutes if you're going for a large number of slices. So that can be kind of a long time to stay still, especially for older people, people that might have some kind of movement disorder, and children in particular. So this long scan time is one motivation for partial Fourier acquisitions. Some others include motivations such as reducing the TE, reducing the minimum echo time to get more signal. This is especially relevant in echoplanar imaging acquisitions where you are acquiring multiple lines of k-space per excitation, and you have to start acquiring lines way before the echo time in the middle of k-space. But if you lop off part of the k-space acquisitions with a partial Fourier sampling scheme, then you can bring the echo time closer, and there are often optimal echo times for acquisitions such as diffusion weighted imaging and functional MRI, where you're trying to get them to a certain point. For example, in bold fMRI, you want the TE to be equal to 1 over the T2 star to get maximum sensitivity to functional activation, but the minimum TE, if you set up a very fine resolution sampling grid, can be pushed past that time. And so partial Fourier is one way to get you back to that shorter time. Same with diffusion. You usually for diffusion you want to ideally acquire signal as soon as you've applied the diffusion weighted gradients. But again, using a long echoplanar imaging readout after those gradients can push the minimum echo time way out. Another reason to use partial Fourier is to reduce flow effects. Because with fewer pulses, you're going to have a smaller total gradient moment. Okay, so partial Fourier acquisitions you can visualize just by truncating the acquisition grid in K-space. So if this is our full grids, it's symmetric, even though my drawing is a little bit lopsided. What I have intended to draw here is a fully symmetric sampling of K-space. If this is our full sampling pattern that we would like to have, and we'd like to, in the image we'd like to reconstruct from whatever acquisition we do, should be the same acquisition should be the same image as from that full matrix. What changes in a partial Fourier acquisition, for example, if we want to reduce overall scan time, what we would do is we would only collect a little over half of the lines in K-space. So you would collect the top half, for example, and the DC lines, and then a little bit past the DC lines into the negative half of K-space. It doesn't matter if you go positive or negative, which side you're on. And then you would leave a certain region completely uncollected. So you'd leave this region uncollected here. In a 2DFT readout with a single echo per TR, another way to implement partial Fourier is to reduce the minimum echo time is to, let's see, let me draw this, is to only sample a little over half of the frequency encoded dimension. So this gets us to a shorter minimum TE, right? So, and you can appreciate that by noting that now the center of K-space, which is where the echo time is referenced to, is earlier in the readout. So you'd be going from here over to here every readout, here to here, here to here, and the echo time now starts much earlier over the duration of each line's readout. And so in this case, the unacquired region is here. So this is two different ways to implement partial Fourier. So it's going to be important in our discussion of how to reconstruct partial Fourier data that we make a couple definitions here. So specifically, a partial Fourier K-space acquisition can be decomposed into two regions. You have first a region that is asymmetrically sampled. That is, it's only sampled in one half of K-space. That is, this range of maximum frequencies in this dashed box is only sampled in one half of K-space, whereas the same range of frequencies in terms of absolute frequencies are not sampled in the other half of K-space. Okay, so that's the asymmetrically sampled region. And then you have a symmetrically sampled region where you do have both sides of K-space. And we're going to denote some bounds here. So we have KY max. KY max will be up here. Then we'll denote KY comma S, where S stands for symmetric here, and minus, so that'll be plus KY comma S, and this will be minus KY comma S down here, which denote the bounds of the symmetrically sampled region. So it's always necessary in practice to collect more than half of K-space to get a symmetrically sampled region for phase correction. That's why we need to do this, and we'll talk more about that later. And the partial Fourier fraction characterizes how much data is acquired relative to a full scan. And on a clinical scanner, there's usually a field for this that you can enter the fraction that you want. And a typical value for this fraction is 0.55 to 0.75. That is, it's always greater than 1/2 because you always collect a little more than half of K-space, and it can go up to maybe 0.75. In the homework, we're going to use 9/16, or about 0.56. So back to our previous scan that we were talking about on the first slide. Now let's say that we do partial Fourier in the KY direction, that is in the vertical, the lines direction, with a partial Fourier fraction of 9/16. What's the new scan time in that case? Well, our original scan time was 256 seconds, And so now we're going to multiply that by 9/16 because that's the total fraction of data that we're actually going to collect. And so that drops the scan time down to 144 seconds, which is a considerable savings. Okay, so we've now defined what a partial Fourier acquisition is, but why is it that we think that we can actually reconstruct a decent image from this reduced data set, where we seem to have violated the principles of Nyquist sampling? So what informs us that we should be able to do this is the Hermitian symmetry of real-valued signals. Hermitian symmetry of the Fourier transforms of real-valued signals. Stated mathematically, this is that if a signal s of xy is real, then its Fourier transform is going to be equal to the complex conjugate of the its Fourier transform flipped across k-space, flipped quadrants across k-space. So that is at the opposite point about the origin in k-space, the signal there should be equal to the complex conjugate of the signal of the signal on the other side. Okay, so let's prove this mathematically. So we'll start with the definition of the complex conjugate of minus kx minus ky. This, by definition, is equal to complex conjugate of our original signal multiplied by the, let's see, we have the original signal complex conjugated times the Fourier kernel minus kx times x plus minus ky times y dx dy. So this is just the definition of the complex conjugated Fourier transform. Then if we apply the fact that s of xy is real, then we know that its complex conjugate is equal to it doesn't do anything. Complex conjugating it doesn't do anything. So we can replace s complex conjugate of xy with just s of xy because it has no imaginary component. But otherwise everything else stays the same. So here we've applied the fact that s of xy is real. Then if we pull out the negative sign from the kx and ky's, then we have s of x comma y e to the minus I times kx times x plus ky times y times dx dy. So here we pulled out the negative sign. Pulled out the minus sign. And of course this is equal then to the Fourier transform of the original signal, s of kx ky. So we've shown this here that if s of xy is real, then the Fourier transform of s of xy, s of kx ky, is equal to the complex conjugate of itself, flipped about the origin. The other direction is easy too. We can start with s of kx ky and go to s conjugate of minus kx minus ky. And we can apply this in one dimension if the other dimension is Fourier transformed as well. And in the absence of field inhomogeneities, flow, motion, and other factors, such as receive coil sensitivities, MR images would be purely real, so we should need only half of k-space. So ideally we would only have smooth phase variations across our imaged objects. If that were the case, we could reconstruct simply by just copying the data and complex conjugating it over to the empty region of k-space, and then taking an inverse discrete Fourier transform or inverse fast Fourier transform to get the image back. Here I've labeled the corners 1, 2, 3, and 4 to note that you need to flip this as you're doing it, right? So quadrant 2 here quadrant 1, you need to flip it about the origin, right? So 1 needs to go down here. You take the data here and put it down here as you complex conjugate it. You take the data here and put it here as you complex conjugate it. and likewise for regions corners 3 and 4. Note, the really important thing here is that you have to take the complex conjugate of the data as you're doing this copy operation. Now this is how we would do it if we had a purely real image, and you can validate this yourself on the computer, that if you take a real valued image, like a real valued phantom image, and then take its Fourier transform, zero out half of it, exactly half of it, and then copy the top half to the unzeroed out portion to the zeroed out portion while complex conjugating it, you would get the perfect image back. But in reality, we do have complex valued images. We do have phase in our images. So next we're going to talk about reconstruction approaches that deal with this in different ways. That's the primary difference between different partial Fourier reconstructions, is how they deal with the fact that you actually do have phase in the image. So you have to somehow try to estimate that simultaneously in the reconstruction as you're estimating that unknown data. So the very simplest thing we can do to reconstruct this data is to just not put anything in the zeroed out region at all. So this is I call this a trivial reconstruction, because you just take the data you have, you put zeros everywhere else, and then you just take the discrete Fourier transform as you would if your original image had zeros in that part of k-space. So a bit of analysis as to why this method kind of sucks will help illustrate the design of the other approaches. And I'll note that yes, it sucks, but it actually is used fairly often, even though that it can incur artifacts. So what have we effectively done in zeroing out this data and then reconstructing it as is? So effectively, what we've done is we've multiplied the data by a step function that is offset here. So specifically, it's offset by the partial Fourier fraction, right? So if we denote this total width to be 1, then this is the partial Fourier fraction here, right, where you're measuring from this point, from the positive point here. So this would be like 0.55 or whatever your partial Fourier fraction is. Now, we've multiplied the data by a step function. So if we look in one dimension, this is the step function that we're multiplying by, and it's the weighting function that we're applying in the ky direction in this depiction. You know that if we multiply a signal by another function in the Fourier domain, we convolve it with the Fourier transform of that function in the original domain, in the image domain. So to understand what this does to our image, we have to take the Fourier transform of this weighting function, of this step weighting function. And if you look at that, you get a function that has both real and imaginary components. It has imaginary components because it's offset because it's not symmetric in k-space, even though it's real valued. And the components basically look like a sinc function plus a delta function in the middle, plus this large imaginary component. And by analyzing the even and odd components, you can actually derive expressions for these analytically, but you can appreciate that with all this ringing, you're going to have a lot of blurring in the image if you convolve your image by these functions. And so that is clearly not awesome. So by the Fourier convolution theorem again, the image is blurred. When we do this zero filling reconstruction, the image is going to be blurred in the y dimension by this function. And if you look at the Pauli partial Fourier reading that you had that was assigned for this lecture, in figure 5 he shows an example image using that approach. Okay, so the second approach is phase correction and conjugate synthesis. Here we're going to call this PCCS. So to eliminate the blurring, what we really ideally need to do is to fill in the missing data, of course. Then that step function, of course, will be converted to just a weighting of 1. It won't do anything at all to the image. But first we have to phase correct the data so that the data we have is that becomes Hermitian symmetric. Or in other words, that the image is real valued, right? Since a real valued image will have Hermitian symmetric data. So what data can we do this phase correction with? Well, the answer is the portion of k-space. We have the portion of k-space that is symmetrically sampled, and herein lies the motivation for acquiring a little bit more than half of the k-space data in a partial Fourier acquisition, is that we get this symmetrically sampled region that we can use for phase correction. Okay, so what you do is you take this small region of K-space, the symmetrically sampled region, you take its inverse Fourier transform, and you're going to get an image that's full resolution this way and low resolution this way. You take its phase angle, so that's what's denoted by this angle sign, so that is, you calculate the phase angle of that low resolution image, and then you calculate a phase correction function that is equal to exponent of minus I times angle of ms of xy. This is your phase correction function. So it's important to note that this is a low resolution approximation to the image phase. So finer phase features will be partially lost. That is, what we expect to happen to them is that they will not be fully brought back into the real channel of the image. Not be fully brought back into the real channel of the image. So after we apply the complex conjugate phase to the image corresponding to the collected data, they will be at least partially lost. Because as you'll see on the next page, we take the Fourier transform to do this reconstruction. We calculate the low resolution phase image, and then we also calculate the Fourier transform of the image, the zero filled image. We multiply the zero filled image by the phase correction function, and then we go back to K-space. Then we take the real part of the result and go back to K-space. And so when we do this, we multiply by the low resolution function, then we take the real part of the result after that multiplication. And so finer phase features will be at least partially lost when we take that real part. So back to the algorithm though, we apply the phase correction function to the partial K-space data in hopes that it will remove all the phase, of course accepting finer phase features that will be partially lost. Then we discrete Fourier transform back to K-space and we fill in the missing data, the data with zeros, using Hermitian symmetry, right? So next I'll show you the algorithm flowchart, but first let's talk about one other problem that you run into with this reconstruction, which is that since the phase correction multiplication in the image domain corresponds to a convolution in the K-space domain, we get errors on the edge of the collected data due to averaging with zeros. So here what I've illustrated is let me undo that. Here what I've illustrated is the Fourier transform of the phase correction function. Since the phase correction function is low resolution, it'll be narrow in the frequency domain, and as it passes over the step function that's applied to the K-space data, you're going to get ringing. You're going to get ringing here at the edges, and that's going to give you these errors there in K-space. Okay, so here's the overall flow graph for this. You take your original data, you take your original data and we'll call this M sub pk, this partial K-space of kx, ky, that's your collected data. Here the shaded region is the collected data and the unshaded is the uncollected. You first zero out the asymmetric part, and then that leaves you just the symmetric K-space data. You take an inverse Fourier transform and you get the low resolution image that we're going to use to get the phase correction function. At the same time, you directly take the discrete Fourier transform, inverse discrete Fourier transform of the original collected data. So this corresponds to a zero-filled reconstruction of the data. Then with the low resolution image, you calculate its phase angle and you generate the phase correction function according to exp of minus I angle, exponent of minus I angle ms of x comma y. You multiply that phase correction function with the image to remove nominally all of the phase in the zero-filled reconstructed image. That gives you this phase-corrected partial data image. Then you go back to the k-space domain, so that'll give you do another discrete Fourier transform to go back into the k-space domain. You get something that almost looks like the original image in terms of support, or the original k-space in terms of where your signal energy is, although there's going to be a little bit of blurring into the uncollected side, again because we are convolving. When we do this multiplication with the phase correction function, we're blurring some of the energy of the acquired region into the unacquired region. So anyways, after we take that discrete Fourier transform, we get the phase-corrected partial Fourier k-space data. Then we apply conjugate symmetry to take the data that we have and project it to the other side, complex conjugating along the way. That gives us our estimate of the full k-space data. So this is full k-space data that is phase-corrected. Then we take the inverse discrete Fourier transform and take the real part of the result of that to get our desired image, mxy. And if all of the phase features are low resolution, they will have been captured here, and so we should get a perfect reconstruction back. The third partial Fourier reconstruction approach is homodyne. And in addition to having a really cool name, the homodyne algorithm eliminates the last two discrete Fourier transforms of the phase-corrected conjugate synthesis algorithm by effectively synthesizing the full k-space before doing phase correction. So to understand the algorithm, we need to think about symmetry properties of the Fourier transform. So we recall that the effective real valued weighting function that is applied to our fully sampled image in partial Fourier acquisitions is this step function w of ky that's offset from the center of k-space, right? So if we look as a function of k-space line, we're weighting very negative k-space lines by 0, and then it suddenly steps up and we're acquiring lines from some still negative point up to the positive points in k-space. Let's also recall that this function has a Fourier transform with both real and imaginary components, which are convolved with the fully sampled image. That's what gives us the terrible blurring in the phase-encoded direction of zero-filled partial Fourier reconstructions. Now, assuming that the original fully sampled image was real valued, and that after our reconstruction we will take the real part of the result, of the reconstruction result, since our assumption is that the imaginary part of the image only contains artifacts, we then only need to consider the real part of the weighting function's Fourier transform. And that's because if we take the real part of its Fourier transform and we multiply it by the imaginary part of the image, then we get an imaginary component, which we're going to discard. If we multiply the imaginary part of the weighting function's Fourier transform with the real part of the image, we also get an imaginary part we're going to discard. And if we multiply the imaginary part by the imaginary parts, we get something close to 0 because we're assuming that this would normally give you a real valued signal, but it's going to be close to 0 because we're assuming that the imaginary component of the image is small after phase correction. But the real part of the Fourier transform of a real valued signal corresponds to the even part of the signal. So this is a basic fact from Bracewell's Fourier transform book, and it can be proven pretty easily. So by definition, the even or symmetric part of a signal, so in this case we care about the signal w of ky, its real part is given by w of ky plus w complex conjugate of minus ky times 1/2, and its odd or antisymmetric part can be derived as w of ky minus w complex conjugate of ky. This works for any signal ever. This is how you can get the even and odd parts of any signal. Here we're applying it to this weighting function. And so the fact we're going to use next is that the real part of the Fourier transform of a real valued signal corresponds to the even part of the signal. So if you have an even w of ky function, you're going to get a real valued Fourier transform. So if we apply this this even and odd decomposition to the weighting function w of ky, what do we get? We get a sort of hat function here for the even part, where this amplitude is 1 in this amplitude is 1/2, and the boundaries of the 1 region are the symmetrically sampled region boundaries. So this is the symmetrically sampled region. And the odd component also steps in the symmetrically sampled region, and its amplitudes are 1/2 and -1/2. And again, this is the symmetrically sampled region here. I'm denoting with those arrows. So note, now you can see where the spike and the sinc function of the real part of W of ky's impulse response, or Fourier transform, comes from. So that is, you have a spike from the fact that you have a constant function, 1/2. You can analytically, you could decompose this function into a rect function plus a constant function. The constant gives rise to the spike, and the rect gives rise to the sinc component. So that's where the spike and sinc come from in that real component of the Fourier transform of W of ky. Now moving on, though, we now see that the low-frequency symmetrically sampled part of k-space is actually overweighted by a factor of 2. So how can we undo this? Well, we can change the weighting function to something like 0, 0, 0, and then 1 over the symmetrically sampled region, and then 2 for the rest of the acquired data. Note that in practice, you would implement this weighting function simply by multiplying the asymmetrically sampled region by a factor of 2 and leaving the symmetrically sampled region alone. So this is the function that you would multiply your data by. So what are the even and odd parts of this? Well, the even part is just 1. That's what we want. We want a uniform weighting of the even part of k-space. We want a uniform weighting, and the odd part is going to be the same as before. It's unaffected by this weighting. So just to take one step back here, so what we're doing is we are trying to make it so that the part of the we're trying to make it so that when we take the Fourier transform of the image of our image data and then take the real component, we have a uniform weighting of the k-space data that went into that real component. And by applying this weighting function in k-space, we have effectively applied our k-space data by all ones. That is, we've sort of magically, implicitly made up all the data on the other side of k-space for the part of the image domain signal that we care about, which is the real part. Okay, so now we have a uniformly weighted k-space and everything is peachy, right? Well, not quite. So recall again that our phase correction in the image domain is a convolution in k-space. Now so this is a step we haven't considered yet in forming that new weighting function where we multiply the asymmetrically sampled region by a factor of 2. So when we do the phase correction in the image domain, we are now going to have and then consider what that does in k-space, we now have 2 big jumps that are going to be blurred when we do that implicit convolution by multiplying by the phase correction function. So so now we're going to have 2 regions where we have transients as the convolution moves over them. To fix this, we replace that step function with a ramp weighting function of the symmetrically sampled region, and this is what is the preferred approach for homodyne reconstruction. So what we change this to is, instead of doing a step, 2 hard steps, we do a ramp weighting up to the factor 2 weighting. So this is 2, this is 0, and this is the symmetrically sampled region. Whereas before, what we had was, I'll draw with a dashed line, before what we had was this. Now we use a ramp function instead. Now if you look at the even and odd parts of this function, the even part is the same. It's still a constant function as we want, in order that the real component of the image has implicitly uniform k-space weighting. And then the odd component will change, but we don't care about the odd component because that always contributes to imaginary components of the image, which we're going to discard. So the ramp bleeds into the odd component but does not affect the real component. So note now that the odd component is smoother than before. So we're not going to have these sharp jumps that are going to result in transients. So the imaginary part of the Fourier transform of W of ky is going to be less oscillatory, which also reduces artifacts. There are of course, many other weighting functions that you can construct that are also possible that might improve further on these features, or on these characteristics. Okay, so now let's take a step back and look at the flow graph for the overall reconstruction. So we take our sampled image data, again M sub pk, partial k-space of kx, ky, where the shaded region represents the data that we've collected. And then that goes through two different pipes. So in one pipe on the left here, we zero out the asymmetric part, leaving only the symmetrically sampled data. We take the inverse Fourier transform of that to get the phase correction function, which has the same definition as in the PCCS reconstruction of exponential of minus I times angle m sub s of xy. And in the other part of the flow graph, we multiply the data by the pre-weighting function w of ky. So here we would have a value of 2 here, and then this would be a ramp weighting. Then we take that weighted data, and we take its inverse discrete Fourier transform. We apply the phase correction. We take the real part, and that leaves us with the desired image, which is hopefully better than the PCCS image. So note here that we have 2 fewer DFTs than phase correction in conjugate synthesis. We only have here we have 2 total DFTs, and before we had 4. Generally, homodyne will do better than PCCS, especially as the amount of data is reduced, whereas the partial Fourier fraction moves down to 1/2. Okay, but homodyne reconstruction still isn't perfect. To illustrate this, let's think of the case where you have 2 pixels that are close to each other, one of which has a large frequency offset with respect to the other, resulting in a large phase difference. And if that's the case, then the tails of of that 1 pixel's blurred imaginary part are going to interfere with the real part of the other pixel. So let's illustrate this here. So first, I want to define that I'm going to say specifically that I'm going to use a blue color to represent real valued signals, and a yellow color to represent imaginary valued signals. Okay, so the true signal from voxel A, let's say that it's a spike. Okay, and when it's blurred due to partial Fourier k-space weighting, you're going to get a blurred out version of the real component, and you're also going to get a negative component here. Sorry, you're also going to get an imaginary component here, which will have side lobes. Sorry, I want to redraw that. You're also going to have a negative component, or an imaginary component, that's going to be antisymmetric. Now, if they're on resonance, then I'm saying that they're going to be in phase, and so voxel B is also going to be a spike, and if that means then, of course, that it's its partial Fourier version with the partial Fourier k-space weighting is also going to be blurred the same way as for voxel A, so it'll have a similar weighting like that. When we add them together, we're going to get the 2 sort of triangular functions for the real part, and for the imaginary part, we'll again get these antisymmetric functions. When we do phase correction, we will get rid of the when we do the phase correction, we'll get rid of the imaginary part, and we'll just have the real part that we want. And so it'll look okay. There won't be any significant artifacts. It'll be a little bit blurred, but no significant artifacts. Okay, but what if we have what if voxel B is off resonant such that it experiences a pi/2 phase shift? Sort of the worst case. So voxel A is still going to be on resonance. It's just going to be a spike in the real channel. When it's blurred by the partial Fourier weighting, it's going to give us sort of this triangular shape, and then we're also going to get energy in the imaginary channel. Now voxel B, though, is going to be perfectly imaginary. It's going to have a pi/2 phase shift, so it's going to be perfectly imaginary. And when we blur it, now we're going to get the triangle shape in the imaginary component, and we're going to get the oscillatory shape in the real component. When we add these together, we're going to get the sort of triangular real shape from voxel A, and we're also going to have oscillations from voxel B throughout, and then an antisymmetric component. And now when we do, and then we also have the oscillatory component from A, and B there. And so now what will happen is when we do phase correction and then take the real part of that, the imaginary part of voxel B is going to be wrapped into the real component, and vice versa. The real component of voxel A is going to be wrapped into the voxel B component, and we're going to get these spikes here, like these troughs next to the voxels, next to the ideal spikes. So they're going to be blurred out a bit more, and we'll have these essentially these side lobes next to them. Okay, so that is, stated another way, oscillation in voxel B's real response add to voxel A's real part and are not removed by phase correction, which is applied only close to B. Okay, so to summarize, both homodyne and phase-corrected conjugate synthesis perform really well if the underlying image phase is smooth, and thus can be removed by a low-resolution phase correction. The weakness of phase-corrected conjugate synthesis arises from doing synthesis after phase correction. That is because you get the blurring across the weighting function, while the weakness of homodyne arises from effectively doing synthesis before phase correction. So it seems that we can't win either way we do it. So in the next lecture, we'll talk about POCs, or projection onto convex sets, which will alleviate these weaknesses to some degree.